Hello everyone, today we are going to talk about a Sun-like star orbiting a Boson star. For this, let us use the last run by GAIA, which is a telescope that is following the movement of the stars in our galaxy. And in the last run, GAIA observed a very strange system. GAIA observed some kind of object that we are going to call dark object with around 10 solar masses that is being orbited by a luminous star of one solar masses of around 1.41 for the semi-major axis of the orbit. This is a very eccentric orbit of 0.45 and has an orbital period of 188 days. So what Gaia did was observed the luminous star orbiting some unknown object that was not able to detect. And for you to take into account the size of this system, this is the same as having the sun that is orbiting some dark object at more or less the same distance as the Earth to the sun. But we don't know what this object is. There are some hypotheses. One of the first is a binary neutron star system or a tertiary neutron star system, or to have a black hole in the center. Both cases have some problems. Mainly, they are the result of the collapse of a massive star that passes through a red giant phase. And this red giant phase will make the star swallow a lot. And in fact, when the sun starts to pass by the giant phase, it will swallow the orbit of the Earth. So you can already observe that for this star and for an even massive star, it will swallow the path of the luminous star that we observed. In addition, both these objects, black hole or the binary neutron star, are the result of a supernova, and due to the distance between the luminous star and this hypothetical supernova, it will be very hard for this luminous star to survive this phase, even if the luminous star migrated onward inside. So there are some problems like the mass range, in particular for the neutron stars. So 2 neutron stars is not enough for 10 solar masses. We need something more. There is also the formation, like I said, for both the giant phase, the supernova phase, and the stability. So one hypothesis instead of considering known objects like black holes and neutron stars, we can consider some hypothetical object. In our case, let us consider boson stars. So what we expect is the dark object, the central dark object is a boson star. And this is the main objective of our work, is to test if the models that we know of boson stars, these hypothetical objects, are compatible with Gaia observations. But before that, it is important for me to clarify what a boson star is. A boson star is an hypothetical astronomical object that is made out of bosons. And for these stars to exist, one needs a stable boson in nature, a boson that is beyond the standard model. These bosons have to be massive and complex with a global U1 symmetry, and they can be seen as everywhere regular lumps of scalar or vector bosons. So they are basically solitons. They have been shown to be able to form dynamically through gravitational cooling and has been proposed as possible dark matter candidate objects. They will interact very weakly with electromagnetic radiation and not emit light themselves. In fact, the name of the star doesn't come from the fact that they emit light, but by the scale of these stars, these objects. They have the same scale as a star. However, they will be massive enough that they can bend light and create an accretion disk around. But for our case, what we are more interested is for them to bend the space-time enough so that the luminous star is able to orbit it. For this, let us consider the following model for the boson stars. In this case, we consider Einstein matter action for both the spin 0 and 1 classical fields, where the matter Lagrangian for both the scalar field and the vector field, spin 1 and spin 0, respectively, contain a self-interaction potential. And this is very important, as we'll see ahead. For the metric ansatz, we consider a metric ansatz that is compatible with the spherical symmetry, a standard metric ansatz. And for both the scalar field and the vector field, we consider an harmonic time dependence. And this harmonic time dependence is very important since it is able to counterbalance the attractiveness of the self-interaction potential. For both cases, there are an amplitude function. For the scalar field is 1, phi, and for the vector field, since this is a vector field, contains two terms, which are the function of that denominate the radial amplitude of these fields. For the self-interaction potential, we have several possibilities. We can consider a spherical potential with just a mass term, and in this case, it's called the mini Boson star. For the self-interaction potential, we can consider a self-interaction potential with just a mass term. In fact, it can be observed that all the self-interaction potentials need to have at least a mass term, and this case is called as mini Boson star. We can also add a quartic self-interaction, which is known as self-interaction, and a cyclic self-interaction. And these objects are known as Q stars, since this potential is known to endow solutions that are known as Q balls. Q balls are similar to boson stars, however, in the absence of gravity. So they are held together not by gravity, but by their self-interaction. However, as we will see ahead, scalar field is always larger than 1, and thence the cyclic term will have a very small impact when compared to the other two. So we are not going to consider it. We can also consider an axion-like potential. And for the vector field, we can consider both a mass term and a quartic self-interaction. However, it has been shown lately that self-interaction Broca stars are very prone to ghost instabilities. And so we are not going to consider it together with the cyclic term of the scalar field. So with this set, we are able to numerically integrate the set of equations and obtain the domain of existence for all the solutions. Here we can see domain of existence, mass as a function of the frequency of the particle. And we can see that in all cases, the frequency starts at 1, frequency over mass of the particle starts at 1, then has an inward spiral. It is a well-known result that for all the self-interaction potentials, there is the first branch that goes from the maximum of the frequency to the maximum of the mass is a stable branch. This is known as the Newtonian branch, and all solutions here are stable. In addition, the axion-like potential also has a relativistic branch, which goes from somewhere after the first minimum of the mass to the second maximum of the mass. So what we want is to find kinematics, so solutions of this GAIA that are compatible with GAIA observations that are in these regions. For this, let us study the kinematics of the stars. We have to consider the time-like geodesics, and it is very important that we want to consider elliptic orbits. For this, the geodesic condition is as follows, where it has two parameters, the energy and the angular momentum of the orbit, that are unknowns. However, from GAIA observations, we know the velocity and radial position in 2 points. So with 2 unknowns and 2 equations, and knowing that the velocity is 0, we can obtain both the energy and angular momentum of the orbit. However, to simplify, let us consider the ratio of the radius that is dependent on the eccentricity. And with this, we can obtain both the energy and angular momentum as a function of the aphelion radius and the eccentricity of the orbit. So far, we have been considering only geometrized units, so it is important for us to consider to add the physical units now, and to simplify again, we consider the units in astronomical units, years, and solar masses. So what we observe in the case of the GAIA observations is that all the boson stars and Broca stars, so the vector boson stars, have the luminous star orbiting the central boson star in a distance enough so that the luminous star does not cross through any part of the energy density. So first of all, you have to take into account that a big difference between boson stars and both the neutron star and the black hole is that boson star, it's not a sphere, a cohesive sphere, so there is no surface. So there is a region of the spacetime with an energy distribution and matter distribution where the luminous star can cross through. However, these stars are small enough so that the luminous star, in our case, the GAIA case, will not pass by this mass distribution. And so it's as if these stars are just a point cloud, so they can be anything else. In fact, with this, we can observe that this result is compatible for any case. Here we plot the ratio between the orbital radius and the radius of the boson star, and observe that except for very high, well inside domain of existence solutions, the mini boson star, so the boson star with just a mass term, is always the leading term. That is, the Broca star is never a leading term, and in the case of the self-interaction and the axion, that is only a little bit that is well inside the domain of existence, so in the unstable branch. In any other case, the mass term is always the leading term. There is, however, a region for the axion, which in the second stable branch, which seems like to be able to surpass the boson star, so the mini boson star. However, we have not observed it for now, so we will have to decrease even further the coupling function. But still, if you see at the scale, these are always well inside the orbit of the luminous star. With this, we are able to obtain some bounds, in particular for the mass of the boson star. So this is all ultralight particles. And we can also obtain the maximum radius of the star, which in this case is around between 100 and 300 kilometers. So when we compare this to the orbit, which is astronomical units, you can see that there is no way for the luminous star to cross to the matter distribution. So our results are then always compatible, especially in the stable region, are always compatible with the observations made by GAIA. So, however, one should also ask, what will happen if this luminous star crosses through the matter distribution? Even though this is probably not compatible with the GAIA observations, this can be important for future observations. For this, we have two possibilities. Either we increase the size of the boson star or decrease the radius of the luminous star orbit. We are going to choose the second. For 10, if we put the luminous star at 10 times the radius of the boson star, we can see, in this case, the scalar boson star, we can see that the orbit is not perturbed enough, mainly because the luminous star is not crossing a relevant enough matter distribution. However, as we put the star closer and closer to the center, and the luminous star has to touch more, cross more by an energy distribution region, we can see increase in the eccentricity of the orbit and the ellipticness of it, and creating these very pretty orbits and patterns. For the vector star, we observe the same, basically. For a high enough distance, there is no perturbation. However, as we go inside the vector boson star, the orbit starts to get highly elliptic and with high eccentricity. So we have observed that models with dynamically robust spherical boson star can reproduce observation made by GAIA, and that the largest boson star radii occurs in the stable region, and this is compatible still with the GAIA observations. And in all cases, but particularly in this case, the mass is the leading term. We have also observed that the axionic stars may be able to create luminous stars that orbit inside the scalar boson star. However, we have not observed any of that. In this case, if that occurred, orbits will become highly eccentric and precessing, and thence will be ruled out by current observations. So, to conclude, a boson star at the center as a dark object is compatible with the observations. And if we ask if the luminous star can probe the nature of the central object, the answer is yes. Because of the interaction with this energy distribution, the luminous star will have associated eccentricity and precession that can be then ruled out by observations, or can rule out other objects like black holes and neutron stars. So, thank you.